you can mail me or you can suggest me. So immediate response, if I'm not able to respond immediately, so by next day or okay, I will respond your whatever queries or feedback. Even if you give a feedback, I used to reply saying noted and then thank you all. Okay, so we have to note it. But whenever I mail, nobody is responding. So then I assume sometimes everybody has received mail or everybody is not opening the mail. Okay, so we may have to do this since if it is face to face, if you are in the campus, then we know that how many of you are doing. But here online, we are not able to monitor such thing. We have to respond. But uh, very few are responding. Okay, so but whatever it may be, so now let's hope this power system will be a successful online class. Okay, so that's all for the uh, regarding the online class discussion. So now we'll start with our regular session, that is lecture on power system operation and control. Okay, okay, so okay, are you able to see my slide?
No, sir.
Okay, so now, so type changing transformers I have even uploaded the okay, so if you know this much, then it will be good enough for you all. Okay, okay, so now what you can do is, so with completion of the type changing transformer, so we have completed unit 3. Okay, so voltage control and reactive power flow control. So we have completed the unit 3. So now today we will start the next unit, that is unit 4. Okay, actually unit 4 is a second last unit, and the unit 4 is very interesting and then easy also. Okay, so here how to do a real power scheduling and then all. So here it will involve little bit of the numerical mathematical calculation, no formula as such, but basic concept you have to know, and then you do which one is easier and which one is cheapest way to do a real power scheduling, and then all it will be learned. But unit 4 is regarding power flow control, how to control the power flow and the real power scheduling. So already we have learned something about the AGC, automatic generation control. In automatic generation control, it will control the power flow, right? But there is certain limitation which I have not explained earlier. So in this portion, we'll see that what are the limitation of AGC. Okay, so that means automatic generation control has certain limitation. It can control the power flow, but it has a certain limitation which we cannot apply. Okay, but this is general how we can control the power flow using AGC. But now we will go specific how to control the power flow in specific lines. Okay, if there are double circuit line, how to control at the one circuit and then another circuit. Okay, so but AGC will just carry out the overall power flow. Okay, so this we have to learn in unit 4. Okay, so power flow control and real power scheduling. And then today's lecture will be on power flow control, how to control the power flow, and you know why we have to control the power flow. Okay, so now before we start about the power flow, so let's see unit outlines of unit 4. Okay, so unit flow 4 outline is basically there are 4 under that they have given. Okay, so first one is power flow control, how to control the power flow, one using fixed and variable series reactant compensation. So already you know that series and then variable fixed and variable series reactant compensation. Okay, so then another one is phase shifter. Okay, we'll see phase shifter. We'll phase shift. Okay, for three phase, we'll try to phase shift and see how power flow can be controlled. And then we'll see TCSC, okay, thyristor control series capacitor. So this one I have seen you are learning in the all principle learning in the power electronics application. Okay, TCSC. Then another one, so we'll see HVDC links. Already you have learned a little bit how we can apply for power flow control. So under HPDC link, you know that monopolar links is there. Okay, bipolar, and then there are three links which you have learned. Okay, so we'll see that, and then real power scheduling. Okay, so under power flow control. Then when we do a real power scheduling itself, you will be able to know the operational objectives and constraints. When you do a real power scheduling, what operational objective should be there, and what are the constraints. Okay, so if you know these objectives and constraints, then you will be able to do a formulation as an optimization problem. Okay, then you have to formulate as, then we'll know that which one is economical power system operation. Okay, so if we complete this, then we will be completing unit 4. Okay, so under unit 4 we learn power flow control. So how to control, there are different techniques, and real power scheduling. So under real power scheduling itself, so you will know operational objectives. First you have to know operational objectives, then constraint. So after knowing these two, then we have to optimize the problem, okay, or formulate the optimization problem. Then after that, formulating and then solving that, then you will know which system is economical for power system operation. Okay, so this all about the unit 4. If you complete this point, then we will be able to complete the unit 4, and then I feel that unit 4 is very interesting and then easy compared to other module. But I'm not saying other module, other unit are very difficult, but others are also relatively okay. If I am at your position, so definitely for class test I will not choose unit 1. Instead I might have choose unit 3. 3 is very good. You have just waveform, and then you just see that curve increase and decrease, then voltage will be controlled, reactive power will be controlled or injected. So you have to know this much only, but you are more confident in unit 1, that's good. Okay, so if you are more confident in unit 1, so we'll do for unit 1. Okay, so there's the unit outlines of unit 4. So first let's see power flow control. Okay, so under power flow control, okay, so power flow control. Okay, so first under power flow control, so now even now as far as possible, okay, you have to be mindful that as far as possible I am trying to simplify the note. Okay, and then I am not taking more than at the max 20 slide per lecture. Okay, so at the max I'm saying sometimes it will be 10 to 12 slides only. So I'm not taking more than, even in our class I have not taken more than 20 slide at the max. So it will be 20, that is rare case. Okay, so most of time, so real content of the module slide will be either 10 to 15 on. Okay, so now this today lecture we'll see the power flow control, and then even here, so actually these are not required. I have given objectives of today's lecture. What are the objectives of today's lecture means power flow controls. So in this lecture you learn the following, which means basically when we complete the today's lecture, you will be able to learn these 2 points. Okay, first one is power transfer capability of a network may be limited due to inability to control power flow in transmission path, which means that power transfer capability of a network, we'll see how power transfer capability of a network may be limited if you're not able to control the power flow in the transmission path. Then another one is what are the ways by which one may control real power flows. So if you're knowing these 2 objectives, then today's lecture will be a successful one, or you have learned everything about today's lecture. Means if you know these 2 objectives, or these are the 2 objectives of today's lecture under power flow control. Okay, so first let's see that. Okay, so now under power flow, why we have to control the power flow? So everybody will know that why we are required to control the power flow. But normally this power flow control, okay, so normally this power flow control is very important, or it becomes a very important features of an interconnected AC system. Okay, if there is an interconnection, it has become a very important to control the power flow, because from one area 1 and area 2, so they are interconnected. So we have to see how much power it has to flow from area 1 and how much power it has to flow from area 2. Then we have to control, right? From area 1, if it say 300 megawatt has to be flow from the area 1, then we have to see how much it has to be flow from the area 2, so that our total power it flows in our interconnected system should be 500 megawatt. If it's like that, then 300 from area 1, then 200 from area 2, and then make it 500. But how to control later on? But this has become very, very important in interconnected system. Okay, AC system, that power flow control has become very important features in interconnected AC system. Okay, because, and then moreover, this has become very important, and then this power flow through a specific control part has become quite difficult. Okay, which means, so if it is a double circuit line, and then you have a two area network, so then it has become a very complicated or quite difficult to control power through a small specific control path. Okay, means because we have known that as per the Kirchhoff's law, okay, as per the Kirchhoff's law, what it says is this power flow will depend upon the line parameters. So you know what are the transmission line parameter, then topology of the network. Okay, then another one is generation and load location. Okay, so this power flow will depend on these parameters as per the Kirchhoff's law. And then Kirchhoff's law is a well accepted laws, right? Everybody accepted it is an internationally accepted laws. And then power flow in these parts will depend upon the Kirchhoff's law, and then Kirchhoff's law says that it will depend on line parameter, topology of the network, generation, how much it has been generated, load location also it will depend. Okay, so that's why inability to, if you are not able to control the power flow, okay, may result in where some part might be lightly loaded and some will be overloaded. Okay, so if you're not able to control the power flows, so some area it will become a lightly loaded, okay, and then some area it will become a overloaded, which is not good for power system. Okay, so it has to be loaded equally, but if you're not able to control the power flow in an interconnected system, then what it will happen is some part will be lightly loaded and then some part will be overloaded, and then this situation should not happen in a good power system network. Okay, so now with one example, so with the figures I will explain here. So this figure is one, just I have given a one ideal situation. There is two area 1 and area 2, and these two has, okay, sharing the power, which means from area 1 some power will be flow to the area 2, and similarly from area 2 some power will be shared with the area 1. But here just see that area 1 is generating 300 megawatt, load is also 300 megawatt, and then area 2 is generating 300 megawatt. Okay, this is ideal case I am giving, and then load is also 300 megawatt. Here if you see this generation and load is matching, similarly for area A also generation and load is matching, so here no need of power transfer as such, right? Okay, but here just to make you clear how to control the power flow, so then what I have done is here in area 1, from the area 1 generation, so 175 megawatt has been fed to the load, and then I'm bringing power from the area 2 generation 125 megawatt, and then this is how we are fulfilling the demand. Just we have made like this, but even if you're not sharing also it will fulfill. Okay, but for our reality and then all we have to do it. Okay, but here this ideal case. Similarly from area 1 area 2, so I'm just taking 175 megawatt, and then from area A, so I'm bringing or sharing 125 megawatt, and I'm trying to fulfill the demand. Okay, this is how ideal case. Okay, so then if you connect this line like this, area 1 and then area 2, so that is known as tie line, right? If you connect the power with area 1 with its neighbor area B, then that line is known as a tie line. Okay, so tie line here in this case what it happen is this area 1 generation will meet the load. Similarly, area B generation will meet the load. So now we are making this tie line, okay, so to share 125 megawatt each. So this has become unnecessarily loaded. Right? This tie line has become unnecessarily loaded in this case. Okay, but just I have made it this one to make you clear why we have to control. So now we'll see how to control and all. But in this case, in such case, tie line has become unnecessarily loaded. Okay, so this may, now what it happen is, if you do like this may be problem if capacity of tie line is limited. So this tie line capacity will be, it has its own capacity. It will not be as per our wish, right? Every line will have its own capacity, and then this may be a problem. Okay, if the capacity of tie line is limited and one wishes to transfer power from one area to another. Okay, if okay capacity of a tie line is a limited one. Okay, so just now I have said 125 megawatt, and then if this tie line is not able to share 125 megawatt, so what it has happened is this has become one a problem, right? So now there is ways to improve this tie line. Okay, so why it has become a limited? Because this line capacitance will be utilized by unnecessary this loop flow. Means this has become a loop flow only. See here, and then from here again similar case you have to supply to area A. From area A, B it has to supply 125, and then it has become one loop which is fulfilled by area A itself. Okay, but if demand is more, then we have to share. Okay, so now it has become unnecessary. So now this tie line will have its own limitation, or it will have its own capacity, right? So just now we have assumed that it will carry 125 megawatt. Similarly, this two tie line will carry 125 megawatt, but if it is not able to carry 125 megawatt, this tie line, how to go about? Okay, so that our power flow can be controlled, and then we can make it to 125. And if it is able to carry more than 125, so this is lightly loaded now, not loaded optimum, right? Lightly loaded. So now in such case, what to go, how to go about this? Okay, so now we'll see that. Okay, so now in previous module, what we have done is we said that we'll install one automatic generation A here, okay, AGC, automatic generation control, and then we'll try to control the power flow. But in this case, if you install a AGC, what it will do is it will try to control here power, generate and transfer, total power only. So it will not go through this control of this individual path. Okay, so it will not be able to handle individual part. What it will do is it will try to control the overall power flow only. So it's, let's say here 300 megawatt, and then we need 175 here. So then here 125. It will just send here 175, and then it will send here 125, and it will not see the AGC will not see the capacity of this tie line at the same time even this line also. Okay, so it will not be seeing this, but what it says is it requires 175. So from here AGC will try to maintain 175 in this line, and then 125 in megawatt in this line. Okay, so this is a problem with AGC. It will control the power flow, but it will not see the individual capacity of, okay, so of a line. So that's why it has written the tie line power flow control AGC was discussed in previous module, but what it has is it has certain problem. Okay, so while here cumulative power exchange between two areas through both tie lines may be controlled by adjusting the power in area A and B, but independent power flow control in each individual line connecting two lines is not possible by generation control alone. So here what it's saying is, so now total cumulative power flow or means 125 megawatt, and then here 125 megawatt. So 125 megawatt from area A is sharing with area B, and then 125 megawatt from area B is sharing with area A. So this one can be controlled by the installing AGC. Okay, but this AGC will not take care about the individual capacity. Whether this tie line can handle 125 megawatt or not will be not taken care by AGC. Okay, so actually, so in this figure, just now we can see that cumulative power flow is 0. Here you are taking 125 megawatt and then you are giving another 125 megawatt, which means this cumulative power flow in two tie line is 0, and then it can be changed by generated power in one area increasing in another one. So this 125 can be okay. So now I can give change this 125 megawatt in this tie line. Okay, first tie line. Let's see here, you may give 120 megawatt, and then here you try to increase 130 megawatt, and then you try to change this power also. Okay, you can change this, and then we can carry out this. Okay, just changing the generation here. So you can try to do, but this is not the good ways or a practice or a fashion in power system to control like this. However, this power in each line cannot be controlled in the fashion, and it depend on line parameters and Kirchhoff's law. So we says Kirchhoff's law, the topology of the network and all. Generally, we can do this. It's easy way which we can explain, but this is not a good practice to control the power flow. Okay, so therefore, what we need is there should be some special measure in order to control the power flow through these individual parts. Okay, there should be a special measure in order to control the power flow through individual transmission part I have given here, right? So that power flow can be achieved by changing effective line parameter by connection of capacitor. So lump series capacitor means you will connect here capacitor and try to improve the capacity of this tie line. Okay, similarly you will connect the capacitor in series with this tie line and try to improve, and similarly you can see for other rods. Okay, so you can connect the series capacitors and then try to improve, but this AGC will carry out the cumulative only overall. If this tie line require 125, it will supply 125, but it will not check whether this tie line can carry this 125 or not. If it is not able to carry 125, then there should be other ways which we can carry it out. So we can use a series capacitor and try to improve the transmission, tie line transmission capacity to 125. Okay, this is how we have got a history of series compensation of line. Okay, so now series compensation of line, how to carry it out. Okay, actually when we do a series compensation of line, what we are doing is, so it will change the effective reactance of a line by connecting the series capacitor in the line. So let's assume, just now I have not shown the capacitor, but here in this figure, so there is series compensation we have to do. So now let's assume that in this figure, certain power is flowing from this transmission line path. Let's assume this path 1 and another one is a path 2. Okay, so now definitely more power will flow through the part 1 than the part 2, because part 1 reactant is X and then part 2 is double of, which means, so power, you know that power equation. So now definitely more power will flow through part 1 than part 2. But now I want to increase the power flow through the part 2 also. Okay, or make it equal to part 1. How to carry it out? We have to reduce this capacitance. Sorry, not reduce this reactance. How to reduce this? So now we have to connect the capacitance in series. So you know that equivalent resistance, how to find. So this is a inductance and this is a capacitance, how to find. You know that basic equation you have to use, and then you try to reduce the total reactance, and then if you reduce the total reactance, then your power flow through this part 2 will also increase. This is how we do that. Okay, so but if you install the AGC, it will say if this transmission line is require or carry 20 megawatt, so it will just distribute 20 carry, and another one will have a 10 megawatt like this, and then it will not see the capacity of this. Or now if it says 20 megawatt each has to be transferred, then if you have installed a AGC, what it will do is it will try to see 20 megawatt, 20 megawatt, but it will not see the capacity of an individual line. So now to see the individual capacity of individual line, then we are doing the series compensation. Wherever there is a low power transfer, we'll try to increase the power transfer by connecting a series capacitors. Okay, so this, so now if you connect this, okay, so here I have explained figure 2, the power flow in branch 2 with reactant X2 can be increased by compensating with the series capacitors. So definitely, so this will have a low power transfer or flow because of this reactant, and then the part 1. So now how to improve is you try to connect the series capacitance. Okay, so that your total reactance will be reduced and then power transfer will be increased, and then this is how you are trying to optimize so that whatever generated here, so you will get it here if you do this. Okay, or less losses will be here. And then if you connect this, okay, this series capacitance, first characteristic is it will change the effective, okay, change the effective series reactant of a line. Okay, so series reactant of the line will change. Another one is reducing the line reactant means it will improve the stability of a system. So for good quality power, it should be stable. One thing is should be stable. So what it will do is if you connect this series capacitance, then it will improve the stability of the system or a power system. Okay, so this one I have explained, but this series capacitance should have a property. Okay, it should have a property when there is a fault, or here I have written since the amount of loading changes with time. So here load will be a dynamic, it will keep on changing. This amount of series compensation may be varied by bypassing or shorting out this capacitor when it is not necessary. So now if it is not necessary, let's say here power required is less, and then if it is not necessary, then we can remove this or shorting out, that whatever power it can handle, it can allow to pass. Okay, okay, so this series capacitor should have a property such that whenever it is not required, it can has to be bypassed or sorted out. Okay, so that's why it is written varied by bypassing or sorting out this capacitor when not necessary. So if it is not necessary, it has to be sorted out or sorting out or bypass this, and then whenever it is required, it has to use that. Okay, so that our stability will increase and maximum power flow or power flow will also be increase. Okay, so this is the property of series capacitor. Okay, so which we can improve the power or power flow can be controlled by inserting a series capacitors. Okay, this is first ways which we can control the power flow. And then another way is by using a power electronics device also we can control the power flow. Okay, so this one we have learned in the earlier lecture. This is a TCR, terrestrial control reactor. Okay, if you connect this terrestrial control reactor in parallel to the series capacitor, so there will be a number of capacitor, one will be fixed, another one. Okay, so if you connect this TCR in parallel, okay, so parallel to the series capacitor, so now is effective control, is effective reactant may be controlled by controlling the firing angle. So now what you can do is if you do this, so here depending on the firing angle your effective reactant will be controlled. Okay, so firing angle delay and all, so it will control. Okay, so such type of device is known as TCSC. Okay, so TCSC means terrestrial control series compensator. Okay, so this is also another ways to control the power flow in the transmission line. So what you can do is you have a series capacitance, then you connect this TCR in parallel with the series capacitance, and then you will get one device which is known as TCSC, terrestrial control series capacitor. So now for terrestrial control series capacitor is characteristic and the working principle. I have seen you have learned this concept in the power electronics application. Okay, and then even more than this one, you have learned that other types of fax device. Actually this will fall under the fax device. Okay, so there are two ways which we can control the power flow. First one is connecting a series capacitor directly to the line. Another one is by using a power electronics device, which means power electronic device means a thyristor. TCR can be connected in parallel with the series capacitor. Already it is there in the series capacitor connected in the line. So you connect parallel this TCR, then we can control. But this device has been named at thyristor control series capacitor. Okay, so now how it functions, the thyristor control series compensator or capacitor, some call it as a capacitor compensator. So how it function is, so now, okay, so now in such case, so most of the thing is we have to reduce the effective reactance. If you reduce the effective reactance, more power will be flow there, right? So now how to reduce this? So now already you have learned that if a circuit involving inductance and capacitance, so you have found out that resonant frequency Fr is equal to 1 by 2 pi under root of LC. Somehow like this you have learned, right? Resonant frequency. Okay, so you might have learned this, how to find this resonant frequency in the CTN, circuit theory and network. So similar case here, when we talk about the thyristor control series capacitors, it has a capacitance and then inductance. So in such case, if you keep on changing the firing angle, okay, firing angle alpha of a thyristor, then it will reach one condition where there will be a resonant or parallel resonant point. So we call it as effective reactance is a parallel combination of fixed capacitor and variable reactance. So and then parallel resonance may occur at certain values of firing angle. So now you keep on changing the firing angle, and then at one point you will reach a parallel resonant points. Okay, well, you might have already studied about the parallel resonance. So you will reach a parallel resonant point. So in such case, what you can see is, in this case, maximum power can be transferred or a power flow control can be carried out. All right. So that's why I've written the characteristic of TCR is shown here. So now alpha you have started with certain angle. So total. So let's say alpha equal to 80 degree. In the x-axis is a firing angle. Y-axis is a TCSC characteristic like reactance here, and then other one will be capacitive region. Okay, so reactive and the capacitive region. So in such case, what you have to do is, okay, when you keep on increasing or changing the firing angle, so it will reach a point where your resonant, or we call it as a parallel resonant point, where both inductors and a capacitor will start functioning or operating. So in such case, so what we can see is, so maximum power can be transferred. Okay, so one of the major consideration of any series connected device, so now is to bypass the device when, okay, so in such case what you have to do is, so now in it has to bypass the fault, okay, occur nearby, which means if there is a fault, this compensator should not function. It has to bypass the fault, and then as soon as the fault is clear, so this compensator or has to function again and then bring the system to the stability. Okay, so that's why it is written major fault current cause overcurrent in a line, which in turn result in over voltages across the capacitor. So this will have a bad effect on our compensator. So as soon as fault is there, what it will do is it will bypass the fault, and then as soon as a fault is clear, and then it will try to function, and then it will bring back to the stability. Okay, so in order to do this, so most of time you will see that it is combination. Okay, so it is thyristor control. It will have a combination of metal oxide varistor and then circuit breaker will be connected across the device, so that if there is a fault, it will be bypassed, and as soon as the fault is clear, it will be connected there. Okay, so which means you have to know that series compensator has to bypass during the fault, and immediately if fault is clear, it is necessary to insert the maximum capacitance in order to improve the stability of rotor angle deviation which occur due to the fault. Okay, so this is something about the thyristor control series compensator. So here I'm not explaining about the how it working principle of thyristor control series compensator, because I've seen you are learning in the power electronics application, even waveform and then all I have seen that you are learning. So here, just I want to see that how to control the maximum power flow using the TCSC. So in TCSC, when you keep on increasing the firing angle, it will reach to a certain point, that point where both the inductance and capacitive region has to function. Okay, so in that point, so that point is known as parallel resonant points, and then maximum power can be transfer. And then general characteristic of this compensator, series compensator, is it has to bypass the fault. Okay, whenever there is fault, why we have to bypass it? Because so if you're not bypassing, then there will be overcurrent in the line, and then which will result in over voltages across the capacitor, and then our capacitor will get damaged. So now that's why you will see that most of the series compensator has a metal oxide with varistor and a circuit breaker connected across series connected device to bypass the fault. And then as soon as fault is clear, it has to be functional, or it is necessary to insert the maximum capacitance in order to improve the stability of rotor uh, angular deviation, which due to the fault there is some disturbances. Okay, so that's about the series compensation. There are two ways which we can carry it out. First one is just a capacitor you connect in series, then another one is using a power electronics device, power flow can be controlled. Then another one is we can also change the power flow, either increase or decrease the power flow by using a another types of power electronics device, or by injecting a variable voltage in a series with a line through the transformer. Okay, so now similarly another way to change the power flow or power flow control can be here. Earlier one we have connected one series capacitor, then second one what we have done is we have connected TCSC, and then third one is you just inject here variable voltage in series here, and then you can try to change the power flow. When it require more power to flow, you inject the voltage, because power is equal to VI cos phi. If you increase the V, definitely power will also increase. Or if you require less power, then you try to remove the power, or you are not required to inject the voltage. So now how to do this is, this can be achieved by using another power electronic device which we known as VSC, or DC slash AC converters. Here VSC, DC slash AC converter. So where you will have a DC source. Okay, this source should be there, okay, first, and then so this DC source you try to convert or rectified, sorry, convert to AC, and then this AC will act as a variable voltage source, and whenever it require, you inject here and then try to increase the power flow or change the power flow depending upon our load. Okay, so this is known as uh, this is another ways which we can control the power flow or change in the power flow. So this type of devices like VSC and then TCSC, or the device shown in figure C like VSC, is known as FACS, Flexible AC Transmission System. Okay, so this type of device is known as a FACS. So if you really want to learn about the FACS device, you can see understanding of FACS device by one book is there by Hingorania. Okay, so but already you have learned in power electronics application. So these devices, such type of devices are known as FACS, or flexible AC transmission system. And why we call FACS? This is because they increase the flexibility of AC system operation by allowing additional control. Okay, what it means? It will increase the flexibility of AC system operation by allowing additional control. Okay, so such type of device is known as FACS. And then, so today, so I will stop here. Okay, so other phase shifting and then all we'll see next class. But today, so what we have learned is we have learned about why we have to do a power flow control. Okay, overall I will say that power flow control, and you know that if you use a AGC, so you can control the power flow, but this AGC will not take care about the individual capacity of an individual line. So which is a limitation of the AGC. But overall cumulative it may be controlled by the AGC, but it will not see the individual capacity. So example I have said here is if one tie line is not able to carry 125 megawatts, let's say only 100 megawatts. So 25 megawatt is not able to carry by these tie lines. In such case, what you have to do is you use some compensator and try to improve or decrease the reactance and improve the power. Then how to do is there are different ways. Okay, series compensation, just connect one capacitor and then try to reduce this inductance. You know, if I connect a capacitor here, so total reactance will reduce or decrease. We have to see that, and then power can be increase or decrease. Means we are changing the power flow, means power flow, which means we are controlling the power. Then another way is you use a power electronics device that is known as TCSC, and then we can control that. Then another one is also we can control by using another type of power electronics device or just injecting the variable voltage in series, and then this can be done by using a power electronics device which is known as VSC, DC to AC converter. So here it should have a DC source, then this VSC will convert DC to AC, and then it will act as a variable, and then based on that our power flow in the transmission line can be changed. Okay, so that's all about today's lecture. So tomorrow we'll see phase shifting transformer, how we can control the power flow using a phase shifting transformer, and then towards the end we'll see another type of power electronics device, AC DC AC conversion. So there are a lot of advantages of AC to DC conversion and back to AC. That's why you might have seen now most of the research is going on DC transmission system. Okay, so from here little bit you will understand why we are going to the DC transmission system. Okay, so that's all about today's lecture. So tomorrow I have to call off the class, but if you are interested, I will share the link. You can attend the seminar, but it is not compulsory. I am saying attend just if you have enough data and if network is good, and then presentation and then all will remain same like what we are doing here only, right? But only thing is it has become a virtual only, so we will not meet face in real face, just in a virtual they will present, and then some of us will ask question, and then based on that we will evaluate. Okay, so that's all about today's lecture, and then if you have any doubt, so anytime you can write to me either through social media or WhatsApp or whatever it may be. So I'm ever ready to help you. Okay, so at any cost or even at the midnight, I will answer you. Okay, so that's all for today's. So thank you for coming online. And then tomorrow,
Thank you, sir.
so
Thank you,
I know
sir.
that you will get free. Okay, so
Thank you, sir.
that's all for today.
Thank you,
And then
sir.
Thank you, sir.
Thank you,
hope,
sir.
hope all of you are staying safe, right?
Yes,
Yes,
sir.
sir. Yes, sir. We are completely safe, sir, right now.
Okay, so I have seen one additional cases today, so everybody are updating on this. Okay, but it is not a community transmission, but it is like just from quarantine facility they have found out, right? Okay,
Yes, sir.
okay, so that's all for today. Thank you for coming online.
Thank you.
Thank
Thank
you,
you,
sir.
sir.
Thank you, sir.